Okay, so hello everyone. I am going to talk to you about databases, but first of all, who am I? So I'm Andrew. I am, as you've heard, a Django core developer. My main job in Django is doing sort of database backend work, in particular Django's migration solution, which we're introducing. And I also work at Lanyard, which is the sort of professional events listing site, in this case, conferences for technical people. Now, a lot of what I do is technical, but I'm also a student pilot. I learned to fly things like this wonderful plane here. And in a way, planes are quite similar to databases. There's four important things. They both contain very valuable cargo. A database contains your entire business, typically your logic, your customers, their billing information, their addresses, and of course a plane contains people who are reasonably valuable. You want reliability. You don't want your plane to crash or engine failure. You don't want your database to stop working. You want it to keep going. You want it to make sure that it's going to have your data 5, 10 years in the future. Faster is better. You don't want a slow database. It's kind of useless. And also, they both have bad failing modes. You don't want the plane to crash, and you don't want your database to crash and lose all your data. They're both very, very crucial. And so this is why databases are important, and they're kind of underappreciated part of programming in many ways. A lot of web programmers know a lot about programming. They know their runtimes. You saw just now in the JRuby talk, performance of code is well thought out, well looked at, benchmarking. But often the same doesn't apply to databases. And so it's very important to make sure that you know what you're dealing with and that your database isn't just a black box. Far too many people think, I can just stuff data in there, magic happens, and then my results come out. And that works fine when you're a brand new company, but as you get bigger, you have to start understanding what's in that black box. And so I'm going to look at four basic areas of how databases work, historically and also today, and then also look at a few of the newer developments, such as asynchronous queries and such. So the key thing is databases have been around since the 1960s. They're around half a century old. The very first ones came from mainframes. They were designed to store things like airline tickets. American Airlines had one of the first databases in the world. And so the first relational database, ones with tables and non-tables, came in around the 1970s. Before that, databases were much more unordered. They didn't have proper relationships, and so they were actually NoSQL databases. They're in fact older than relational ones. In the 1980s, SQL came along. A group of people decided that having loads of crazy binary formats to query was a bad idea, and so we got a reasonably decent standard that is SQL. It's a bit crazy still, but it was a lot better than what came before. And so throughout this period, databases transitioned from mainframes, from the likes of IBM and eventually Microsoft, down to personal computers and standard hardware. But a lot of that mainframe heritage stayed for a while. In particular, the idea of journaling. So the main point of journaling is that if your database exits with a crash, if your machine powers off, if your entire data center loses power, your data is safe. Now, that may seem like a simple thing, but if you think about writing to more than one file, if you've got a query that writes to two files, say an index and your main store, and you write to one of them and the power goes off, that's now inconsistent. If you boot that up again, they don't match, and suddenly things will start to go wrong. And so the idea of journaling, or WAL, which means write ahead log, is to make sure that when you write data, that either all the data is written or none of it is written, so it's always consistent. This is the C in ACID, in fact. And so generally, with journaling, this is done by writing changes somewhere else first and then putting them on the main database, or vice versa. With WAL write-ahead logs, every time you do a transaction, you write to a log first and then to the main store. This means that if the whole thing crashes, you can then take your main store, replay parts of the log, because they contain what you just did, until you get back to where you were. Now, this seems simple enough until you consider how computers work, which is badly. So, you probably think you go, database, it's talking to your disk. That's not necessarily true. There's an OS in the way. And operating systems love caching files. They love caching files. There's a reason that your OS is so fast at certain things. It caches files in RAM, it caches saves in RAM sometimes. It just does all sorts of crazy things to get that file system access really fast, because disks are really slow. And so if you're writing through the OS, you have to do something called fsync to ensure it flushes to disk. That's fine. But you've also got a disk controller. Your disk isn't just a spinning platter or an SSD. It has a small chip in it, and that chip has cache as well. And so when you do writes, they may not actually go onto the disk. And they might be sitting in the RAM, and then if you lose power, if they've not gone all the way through the disk onto the actual storage, you lose them then as well. And of course, that's just, if you've got RAID, you've got a RAID controller doing other shenanigans as well. If you're on EBS, you've got network cards in the way in all manner of layers. And so it's very difficult to get that kind of stuff working correctly. Now, fortunately, most modern ones do. Some of you may have had crashes in the past. Generally, MySQL recovers sometimes. Postgres recovers most of the time. Generally, sort of the better designed the database, the better it recovers. And it all depends on how they do that kind of stuff. But you've got to think about that kind of problem. And this is why sometimes writes are slow. One of the big things about MongoDB when it first came out is that Mongo didn't do proper write journaling. If Mongo crashed, it lost some amount of data in the history. These days, there's options to fix that. They're improving it. But that was one of the reasons they were so fast at writes initially, was that it was writing, but not necessarily actually writing, just kind of writing. So you have to sort of be aware of what kind of trade-offs you're making. Now, the second part of databases, and one of the more important ones for sort of complex business logic, is transactions. Now, transactions sometimes are misunderstood. They're a useful way to do things. They wrap around stuff. But what they're actually for is isolation, which is the I in ACID, incidentally. So a transaction is a way of collecting a group of statements, typically some writes and some reads, and telling the database that these are all one process. These should see the same consistent database. This is particularly important when you see here, you've got transactions T1 and T2. They're both doing reads, and they're both doing writes. Say, for example, those two reads were, find me the maximum ID in this table, and those two writes were, write a new row with the maximum ID plus 1. That's going to fail like that, because they're both going to read the same table, get the same maximum value, and then write the same maximum value, and it's going to clash. And so what transactions do in databases is internally they do what's called serialization. They will try and run your transactions in a way that means they're actually technically look like they run one after the other, even though they're probably parallel. So, for example, it could reorganize them like this. So you can see that it would push the write, or the read rather, back past the write, with a write lock in this case. But those two reads are fine because they can just read the same table and that's consistent. And so a good transactional system will sit there and reorganize your queries so they all look like they're accessing the same database linearly so you can stay sane. But that also means that you get slowed down. So if you're doing a lot of writes to a table, especially the same rows of the table, then you're going to hit all the locks and those reads are going to be pushed back. You can turn off transactions, but be aware that if you're doing any kind of sort of selling logic or financial transaction stuff, be very cautious because you can very easily overwrite yourself or read the wrong thing twice. And so just be aware that if you turn off transactions, it's your job to do this kind of stuff. You have to do your own locking if you think that's sensible. Altering schema, which is my bread and butter, I suspect. So typically, databases store data on disk as a set of one or more files with actual data in them, the column values. And some way of describing the schema, and separate index files as well. And typically, in something like an ISAM format, say my ISAM, that's just literally a file full of sets of data one after the other linearly. And so say you want to add a new column to this file. So that's all well and good if it's an optional column. Because it's an optional column, you can just say, the schema, optional column, and just leave all of those entries blank. There's no need to write to that file at all. It's optional. You can just not put the entries in there. But if it's got a default value, or it's some other way, it's non-optional, your database has to go through and write every single row in that file, adding the new default value. And this is why if you add a column with a default, or in fact in MySQL, if you add a column, it takes a long time. It has to write to every single row in your database table. And so you should be aware of this. Changing your schema may not seem particularly slow at first. when you've got, tens of thousands, hundreds of thousands of rows. But when you've got, millions and millions of rows, it takes time. For example, at Lanyard, we have a table with, I think it's 7 or 8 million rows in it. That took 15 minutes to add a column on MySQL. We have since moved away from MySQL, mostly for that reason. But that illustrates how slow it can really get. And finally, joins. Now, as we all know, joins are evil, right? They're horrible. They're the reason NoSQL is so popular. Why would you ever think about doing joins? Well, there's a very good reason. Joins are, in essence, a very simple thing. They take every single row in table A, every single row in table B, and then for every row here, they look at every other row here. Now, I'm sure many of you realize that this is n squared. It's ridiculous. If you've got a million rows on one table, a million rows on the other table, that's a billion, no, 1,000 billion technical comparisons. That's crazy. But of course, fortunately, we have clever people doing databases, and so they've invented ways around this. In particular, index scans, which means that for every row on the left, you can just do a quick index scan on the right rather than looking through all of them. Merge joins, which do things like they sort both sides and do basically all kinds of merge sort interaction. And hash joins, hash tables are just fast. It just does quick hash lookups. But the key thing here is that you're probably doing joins even if you're not doing them. If you're doing a NoSQL solution, often you'll find yourself getting one set of integers from over here and then finding that set of integers in another table. That's a join, that's the same thing. And in most databases, if you do that outside the database, it's slower than doing a join. So joins are actually good if you're using them for the right thing. The key thing here is that you need to denormalize. Don't just join everything blindly. Professors and academics say, you must normalize your databases, have everything stored in one place. That's lovely if you're sort of living in an ivory tower, but the key thing is to make sure that it's fast. And sometimes you have to copy data to different tables, make sure it's in different places. But wait, there's more. Asynchronous calls. This is a relatively new thing in terms of adoption. So as we have asynchronous backends for various programming languages, Node.js has become more popular as well. The idea of asynchronously calling your database has become a lot more popular. And this is very useful because say you're doing 10, 15 queries for a web page. Most of those queries are independent. At Lanyard, we'll probably select your user session, we'll select a couple of conferences, we'll select some users going to those conferences, we'll get some pictures for them. Those are kind of all independent calls. And so you can do them all in parallel. You can fire off your queries at once, have one fixed amount of time, and they can all come back, and it saves you a lot of time. And it's particularly easy in most of the new backends. In Python, for example, in Eventlet, you do it like this. You take the CyclePG, which is the Python Postgres module. You can just turn on Eventlet's monkey patching, a horrific thing here, but it has to be done, unfortunately. And then you can just do 2 connections at the same time, execute them and fetch them. And that's asynchronous. That will do exactly the right thing. Node.js, all the database drivers in Node.js, I believe, are asynchronous. I'm not sure about Ruby, but I'm sure there are some. And so, it's one of those weird things that's not quite normal to people at once. They expect sort of, in a web server, your request response one thread. If you think about it, you can really sort of save time, not only with this, but if you're doing sort of URL calls or external calls, you can utilize those as well. So just sort of try and keep that in mind. Document stores. Now, these are a new thing to be popular, but they're quite old. Document stores have been around for a while. CouchDB and MongoDB especially have become more popular in recent terms. Now, they're really good for the things they're good at. Document stores, I think Mongo in particular is very good for writing a small collection of documents and incrementing numbers in them a lot. It's good at that. It is not good at storing millions of things and changing all frequently. That's a relational database's job. In particular, they tend to be easy to add data. You send them a JSON dictionary or just send them some data. But they are technically schemaless, but you still have a schema. Your documents, your JSON is still in a format. There's still something there. And if you change that schema, you then have to write code to deal with both versions. We had a Mongo store with like 4 or 5 different versions of the same data in it. Our code to read that was full of ifs, else ifs, to try and work out what exact version we were reading. And so you do pay a penalty for that upfront schemalessness. You can fix that by doing essentially a migration on your schema, but that's also slow. Generally, accessing and touching every record in one of these databases is quite slow. You can do it, for example, in, say, Mongo with a MapReduce JavaScript query or something, but it takes time. So, be aware that they're not as curated. And distributed databases, these are even more popular as scaling is more of a thing. In particular, the fun thing here is the CAP theorem, which is consistency, availability, and partition tolerance. Now, the theorem states that any distributed database can have 2 of these things, but not all 3. In particular, let's take, for example, something like React. React is fully available. So available means that if one of the nodes goes away, then the database still works. It's partition tolerant. If you take away 2 classes and put them together again, it's fine. But it's not consistent. You can read different things from different servers instantaneously. And so if a database ever claims it has all 3 of these, be very, very wary. They don't. They have 2 of them, and they're lying about the 3rd one. I've seen several sort of small startups and sort of buzzword-filled companies go, oh, yes, we have this wonderful database. It works everywhere. It's fine all the downtimes. It's perfect. But then you find out it's not partition tolerant, for example. So be aware of which one of these trade-offs you're making. Generally, people will ignore consistency because in most web applications, in most practical things, consistency isn't a problem. Consistency usually means that they'll match within a couple of seconds, which is fine for most sort of user click flows, but just be aware. If you're doing, again, financial transactions, you really want consistency there. And so also, I want to see sort of a few performance tips. How do databases treat your stuff, and how can you make that better? First of all, please don't use MySQL. There's a caveat here. If you know what you're doing, if you've basically written databases before, and you know that you want it, it's fine. MySQL is a very good, slightly relational data store. It is not a very good relational database. It does not have good foreign key support. It does not have good transactions. It does not have good schema alteration. But it does have quite fast read and writes. And so there are a lot of sites using it at big scale successfully, but most of them are using it as sort of a storage layer for their own kind of database on top of it. All they're using it is basically a schemaless store. A lot of this stuff is basically, it's a very good starting point, but you have to do a lot of work. Something like Postgres will ship with all the functions out of the box. The Postgres guys are very intelligent, scarily so, in fact. They do stuff. If Postgres is slow, there's a special mailing list where you can send the slow query, and they just fix it in the next version. It's slightly mad. But it's other things. So MySQL, for example, it's very fast to start with. There's one thing, it's very fast, and it stays at the same speed. Postgres, as you add more cores, just gets faster linearly. You can give it 64 cores, it will use all of them. MySQL will use about 4. And also, as data increases, the similar kind of thing. MySQL just gets slower and slower, Postgres just stays there. So my number 1 tip. Interestingly, Lanyard, we just completed a move Tuesday last week from MySQL to Postgres. Is possible. It took us about an hour of read-only mode. We have a mode like that on the site. We have a blog post about it, in fact, which you can see on the Lanyard blog. And it's difficult. It took us about a week of engineering preparation, a full day of preparation, doing it and cleanup, strategies. We have around, 50, 60, 70 gigs of data transfers. It's not small, but it's possible. So don't think that because you're stuck on one, you can't move, but just think about this before you get too big. Play to your strengths. One thing I always stress in a lot of talks I give is that there is more than one database. You can run more than one. In fact, you probably do. For example, Solr and Elasticsearch are databases. They're just very good at searches. And so make sure you do what the database is good at to that database. For example, if you're doing lots of full-text searches, don't do that against MySQL or Postgres. They're not that good at that. They do them, but they're not very good. Elasticsearch and Solr are really good at full-text search. That's what they're built for. They're really fast at it. But don't do mass queries by numbers in those ones. It's things like Redis, for example. Redis is a very good database for set intersection, for quick storage. It's terrible at doing large amounts of data. And so you're going to know where your strengths lie and play to them. At Lanyard, we use 4 different data store backends for different kinds of tasks. We have a Postgres for most of our main data. We have a Solr for all of our searches. In fact, a lot of conference stuff is powered off Solr because it's good at faceting. We have a Redis for sort of quick store and sort of user set intersection. And we also have I think there's a MongoDB lying around, but that's being phased out slowly. Use indexes. This is very important. Don't just stand there and go, oh, it's slow. We need to move database. This is terrible. Databases aren't super knowledgeable. They can take your data. They're good at dealing with it, basically, but they don't know a lot about it. You need to tell them what to do. In particular, you need to tell them what things you're querying, and how to access those. In particular, say you've got a table full of blog posts, and you want to index on them. You've got to tell your database that you're looking up by the slug a lot, you'll look up by the post date a lot, but the rest of it doesn't care. And then your database will take that information, it will write indexes for ones you care about, and it will leave the other ones alone. The reason it doesn't index every column is that indexes take disk space, they take memory, and they take time. Every index you add makes a write slower. That's one thing to think about. So don't just go and index every single column you have. That's not going to help. It'll make inserts incredibly slow. But if you index just the right things, you get good speed up. And a way to test this is explain. This is on MySQL and Postgres and a few other backends. If you ask the database to explain a query, it will tell you how it's going to run it, which is very important. I think even Mongo does this as well, actually. And so, for example here, say I wanted to explain this select clause. I tell Postgres, explain this. And it says, oh yes, I'm going to do an index scan on the primary key. That's what I'm looking up by. It's be nice and quick. And that's good. Index scans are good. Index scans are quick. They're binary trees. They're really fast. Databases are built to do index scans. They're brilliant at it. If you see this says sequential scan. This is bad. This means you're going to look at every single row one by one, read the entire row, check the constant, and if it's there, it throws it out to you. This is incredibly slow. On a large database, this will take you minutes, possibly even hours if it's really big. So if you see one of these in a query plan, that's bad. In particular, what you want to do is you want to load slow queries, and then the slow queries, take those, explain them, and see what they're doing. Because I can bet you there's going to be some slow sequential scans in there. And this feeds into my next point. Have analytics everywhere. We have, every single SQL call we have is wrapped. There's a slow query log. There's an overall SQL timer. We have 4 different actual databases just on Postgres. We time each of those differently as well. And so we know where our pain points are. We have a few slow queries, but we know what they are. We know why they're slow, and we're working on fixing them. And so you can't solve these problems unless you know where they are. Now, you probably have monitoring your CPU usage or your memory usage. Have the same on your database. Make sure you know what it's doing, why it's doing that, and more importantly, why it's slow. Don't just get that, oh, the site's really slow, we can't fix this. Another important thing is the number of queries. A lot of badly written websites will do thousands and thousands of queries per page load. That's terrible. You want under 100 and preferably under 20 queries per page load. Anything more than that, and you're wasting time in network round trips to and from the database server. Avoid giant inquiries. This is kind of an anti-pattern, especially in the MySQL world, because it is faster in MySQL. But in Postgres, if you say, for example, select from table where, foreign key in giant list of integers, that's very slow. It has to run the query once per integer. A join is much faster. This is what a join is. It happens that MySQL is actually slower at joins than doing this, which is crazy. But just don't do this on a real database. It's slow, and you can fix it with a join much better. And finally, think. When you do code, you sit there and go, oh, perhaps we shouldn't do 3 or 4 nested loops inside each other and do random calls. A lot of people just take their data, shove it into an ORM, take it out again, and just don't think about it. Have a little bit of time thinking about, is this sensible? Are we storing this the right way? If you're always querying somebody's hometown along with their date of birth, put them in the same table. Don't just have them in separate places. For example, we always have somebody's profile photo whenever we show them. So that's on our users table. Even though it's separately another table, we've denormalized it on. And so there's a good thing to just think about what you're doing. Make sure that you know where your pain points are, and you'll probably be fine. Thank you very much. Are there any questions? Oh, fantastic. Excellent. Thank you very much. Oh, one question there.
You mentioned several times MongoDB.
Yes.
And how do you see it in your project? What are the strengths of it? So where to place it?
So the question was, what are the strengths of MongoDB and where would you place it in my project? So I am particularly, I've used it for a couple of years now. I was first introduced it, I think, back in 2009 or so. It tends to be good for append-only storage. In particular, capped collections are good for that. So if you just shove things into it, it tends to be very bad for sort of statistical reads. So you want to select a large number of things by a constraint. And so generally, I've used it for prototyping a lot. It's good. It can be good for that. It can be good for sort of simple storage of things you don't really look at very often. I wouldn't use it for actually storing sort of important data as such, like things the site runs on, because I haven't found it to be good at that. But they are improving. I mean, the main problem is Mongo is still immature. At the moment, it still locks the entire, I think it's the entire collection or in database on every write. So they're working on fixing that stuff, but it's still a bit slow and immature. So as it improves, I hope I'll be able to use it more. Anything else? Oh, yeah.
You talked about asynchronous connections. Can you elaborate on that? So do you have any kind of callback and then get the result with Ajax?
Yeah.
How
So the question was, can I elaborate more on asynchronous connections? So in particular, what that means, it depends on your language. So in Node.js, it will be callback structured. You say, submit a query, call this when it comes back. In Eventlet, as you saw there, Eventlet works by having sort of built-in green threads. And so when you hit something like that, it will just give away control. And so it doesn't look different, but it actually is asynchronous there. What it's really doing there is it's sending off a query and waiting for it to come back as a callback. In particular, because I did execute before I did fetch all, that's doing the separate thing. It's sending off both executes in parallel, and it's getting back the results in parallel as well. Whereas if you're doing synchronously, you have to send off the query, wait, get the result back, then send off the second query, wait, and you can see that's going to be slower. Okay, thank you very much.